August 12, 1944. Normandy, France. 3 American M36 Jackson tank destroyers face a formation of German Panther tanks across an open field at 900 yards. The Panther's crews are confident. Their frontal glacis plate, 80 mm thick, angled at 55 degrees, creates an effective thickness of 140 mm. No Allied tank gun has reliably penetrated it from the front. They've survived dozens of encounters. They believe they're invincible. The lead M36 fires. The shell screams through the morning air at 2,900 feet per second. It strikes the Panther's glacis plate dead center. Instead of ricocheting harmlessly into the sky like so many 75 mm and 76 mm rounds before it, something different happens. The armor doesn't deflect the shot. It doesn't even slow it down significantly. The shell punches straight through, and the Panther erupts in flames. The German crews are stunned. This isn't supposed to happen. Not at this range. Not from the front. Not to a Panther. What they don't know is that they've just been hit by one of World War II's most closely guarded secrets, the American 90 mm T-33 armor-piercing shot, a shell specifically engineered to defeat what Allied intelligence called the most dangerous tank on the Western Front. But this story isn't just about one revolutionary projectile. It's about 3 separate Allied nations, working independently, each developing their own answer to the same terrifying problem. The British created a tungsten dart that could theoretically penetrate even the mighty Tiger II. The Soviets developed a blunt-nosed shell that turned conventional armor-piercing theory on its head. And the Americans? They discovered something the Germans desperately tried to hide, that the Panther's legendary armor was crumbling from within. Before we unravel this untold chapter of armored warfare, if you're fascinated by the hidden technical battles that decided World War II, subscribe to the channel and drop a comment telling us which tank destroyer you'd want to command in 1944. This is the story of how the Panther's front plate went from impenetrable fortress to fatal vulnerability, and how the Allies discovered the shell that made it happen. To understand why penetrating the Panther's front armor was such an obsession for Allied engineers, we need to go back to the shock of first contact. July 1943, the Battle of Kursk. Soviet tank crews reported a new German vehicle that seemed immune to their 76.2 mm guns. Intelligence photos soon confirmed the worst. Germany had deployed a medium tank with armor protection exceeding even their Tiger I heavy tank. The Panther wasn't just heavily armored, it was intelligently armored. Instead of using thicker vertical plates like the Tiger, German engineers had applied lessons learned from captured Soviet T-34 tanks. The front glacis plate was 80 mm thick, but sloped back at 55 degrees from vertical. This simple angle transformed it into the equivalent of 140 mm of perpendicular armor. British intelligence obtained their first technical specifications in December 1943, when a German scout's notebook fell into Allied hands in Italy. The details were sobering. The Panther's armor-piercing rounds could penetrate 138 mm of armor at unspecified angles out to 2,000 meters. Meanwhile, standard Allied tank guns were bouncing off the Panther's glacis at ranges where the Panther could kill them with ease. By early 1944, as Allied commanders prepared for the D-Day invasion, statistical analysis revealed a terrifying reality. Germany was producing Panthers in far greater numbers than anticipated. Intelligence had assumed the Panther would be rare, like the Tiger I. Instead, production averaged 315 tanks per month in 1944, with over 3,700 built that year alone. American tank crews training in England received the grim news. If you encounter a Panther, do not engage from the front. Flank it or call for air support. The standard 75 mm gun on the M4 Sherman couldn't penetrate the Panther's glacis at any range. Even the newer 76mm gun struggled beyond a few hundred yards. The Germans knew they had a winner. Panther crews were instructed to always present their frontal armor to the enemy. As long as they followed this doctrine, they were nearly untouchable. But in laboratories across 3 continents, Allied scientists were about to change everything. Britain struck first in the race to defeat the Panther. Their solution was revolutionary, but it came with a price. In late 1943, British ordnance engineers at the Royal Armament Research and Development Establishment faced a brutal calculation. The 17-pounder anti-tank gun was their most powerful weapon, but even its standard armor-piercing capped ballistic cap rounds, APC-BC in military parlance, could only reliably penetrate the Panther's turret mantlet and lower glacis plate. The upper glacis remained effectively invulnerable. The answer came from an unconventional direction. What if the shell wasn't actually 76.2 millimeters in diameter? Armor-piercing discarding sabot, or APDS, used a radical principle. A tungsten carbide core, much smaller than the gun's caliber, was wrapped in a lightweight aluminum sabot that fell away after leaving the barrel. The result was a sub-caliber penetrator traveling at extraordinary velocity. On paper, the numbers were staggering. The 17-pounder firing APDS could penetrate 256 millimeters of armor at 500 meters and 233 millimeters at 1,000 meters. This wasn't just enough to defeat the Panther. Theoretically, it could pierce even the frontal armor of the King Tiger, Germany's heaviest tank. British firing tests against captured Panthers in 1944 confirmed the potential. At 200 yards, APDS rounds could penetrate completely or knock out armor plugs from the glacis plate. At longer ranges, they defeated the turret and mantlet consistently. There was just one catastrophic problem. APDS rounds were wildly inaccurate beyond 300 to 400 yards. The tungsten core, once separated from its sabot, tumbled and deviated unpredictably. Crews reported they couldn't hit a barn past 300 meters. The muzzle brake aperture was too small for clean sabot separation, and the much smaller impact point made it nearly impossible to observe where shots fell short, preventing gunners from correcting their aim. Worse still, even when APDS hit its target, the small tungsten core often disintegrated after penetration, causing less internal damage than conventional shells. APDS gave British tank destroyers and Sherman Fireflies a fighting chance against Panthers, but only at ranges where the Panther could kill them just as easily. While the British wrestled with APDS accuracy, the Soviet Union took a completely different approach to the same problem. In late 1943, the Red Army fielded the IS-2 heavy tank, mounting the massive 122mm D-25T gun. This wasn't a high-velocity anti-tank weapon like the German 88mm. It was a modified field artillery piece firing shells that weighed 25 kilograms each, more than 3 times heavier than Panther rounds. Initial battlefield reports were promising but inconsistent. The BR-471 armor-piercing shell could penetrate the Panther's side armor from absurd distances, over 3,500 meters. But against the frontal glacis plate, results were maddeningly unpredictable. Soviet firing tests in September 1944 at the Kubinka Proving Grounds revealed why. When they adjusted propellant charges to simulate combat velocities, a BR-471 shell cleanly penetrated a captured Panther's glacis plate at the equivalent of 2,100 meters range. Yet German tests using the same captured Soviet gun reported zero penetration at any distance when the Panther was angled at 30 degrees. The contradiction made Soviet ballistics experts furious. They examined the shells under microscopes and discovered the problem. The BR-471 had a sharp, pointed nose, excellent against vertical armor, terrible against slopes. When it struck the Panther's angled plate, it had a tendency to shatter rather than penetrate. Soviet metallurgists went back to the drawing board. What emerged in spring 1945 was the BR-471B, and it revolutionized Soviet armor-piercing theory.
Instead of a sharp nose, it featured a blunt penetrator covered by a ballistic cap. The cap maintained velocity in flight, then shattered on impact, exposing the blunt nose beneath. This seemingly backwards design was brilliant. Against highly sloped armor, a blunt nose actually penetrated better than a sharp one because it was less likely to deflect or shatter on first contact. The BR-471B could penetrate the Panther's glacis plate at approximately 1,500 to 1,600 meters. But by the time it reached frontline units in meaningful numbers, the war in Europe was nearly over. Most IS-2 crews fought the entire war with the inferior BR-471.
America's path to defeating the Panther began not with revolutionary ammunition, but with a sobering battlefield disaster. June 1944, Normandy. The U.S. First Army discovered that German armored formations contained far more Panthers than intelligence had predicted. Tank crews reported that 75mm guns were completely ineffective against Panther frontal armor. Even the 76mm gun, rushed into production specifically to deal with German heavy tanks, struggled beyond a few hundred yards. The M36 Jackson tank destroyer, mounting a 90mm gun, arrived in October 1944 as the American answer. But the standard M82 armor-piercing capped shot still couldn't reliably penetrate the Panther's glacis plate. At 500 yards, it penetrated 129mm of armor angled at 30 degrees. Against the Panther's effective thickness of 140mm at 55 degrees, this wasn't enough. American ordnance officers also experimented with high-velocity armor-piercing rounds, HVAP, using tungsten carbide cores similar to British APDS. The T-30E16 HVAP could theoretically penetrate 221mm at 500 yards. But, like the British discovered, HVAP had crippling limitations. The tungsten cores were in desperately short supply, with most material coming from China. Distribution was severely restricted. Most critically, HVAP rounds performed poorly against highly sloped armor, with a tendency to shatter on impact. In December 1944, testing by the 703rd Tank Destroyer Battalion concluded the M36 could not reliably penetrate a Panther's frontal armor with available ammunition. Tactical doctrine emphasized flanking shots against the vulnerable 40mm side armor. Then American metallurgists had a breakthrough. What if they redesigned the shell specifically for sloped armor, using improved heat treatment and better steel alloys? The result was designated Shot AP 90mm T-33. Unlike HVAP, it used conventional steel rather than precious tungsten. Unlike standard M82 ammunition, it featured enhanced hardness and a carefully optimized nose shape. Most importantly, it was redesigned from the ground up to defeat armor angled at extreme slopes. In January 1945, American Ordnance issued a dramatic report. Complete penetration of the Panther's glacis plate had been achieved with T-33 shot at 800 yards. Later testing confirmed penetration at 1,000 yards. The unknown shell had finally arrived. But something else was happening on the battlefields of 1944, something the Allied intelligence officers initially dismissed as impossible. Reports began filtering back from IS-2 crews on the Eastern Front. Panthers that should have been impervious to frontal hits were being penetrated at extraordinary ranges, sometimes over 2,000 meters. American tank destroyer crews in France reported similar anomalies. Shells that bounced harmlessly off Panthers in July were penetrating cleanly in December. British intelligence documented an even stranger phenomenon. In some engagements, when 75mm or 105mm high-explosive shells struck a Panther's armor, instead of simply scorching the paint, entire sections of the glacis plate cracked, spalled, or even blew completely off the hull. The welds joining armor plates together were failing catastrophically. Allied metallurgists examining destroyed Panthers noticed the fracture patterns in the armor plates.
Instead of the tough, fibrous failures expected from quality armor steel, they saw crystalline, brittle fractures. The armor was shattering like glass. In August 1944, U.S. Army officers conducted detailed examinations of captured Panthers at Isigny, France. What they found was shocking. 2 out of 3 Panthers examined showed catastrophic cracking in their armor plates. Not from combat damage, from manufacturing defects. British examination of a Panther captured in Normandy revealed the glacis armor had a hardness of approximately 272 Brinell. This was adequate, but hardness without toughness is worse than useless. It's dangerous. The armor was hard enough to resist penetration, but so brittle that when it did fail, it failed completely. Soviet metallurgists analyzing captured Panthers reached the same conclusion. They reported in early 1945 that Panther armor showed varying fracture behavior from fibrous to purely crystalline with no consistency between plates of the same thickness and type. The Germans were losing the metallurgical war, and they knew it. By summer 1944, the vaunted Panther wasn't just being defeated by better Allied ammunition. Its own armor was becoming its Achilles heel. The question was, why?
The answer lay buried in German strategic planning documents and resource allocation reports that wouldn't be fully understood until after the war. Germany's armor steel production depended on a precise cocktail of alloying elements: nickel for toughness, manganese for strength, chromium for hardness, and molybdenum and vanadium to control grain structure and prevent brittleness. As early as 1943, these critical materials were disappearing from German supply chains. The Soviet offensive in early 1944 recaptured Ukraine, including the manganese mines that supplied German steel plants. By February 1944, this critical source was cut off. Manganese was essential for preventing iron sulfide formation and increasing hardenability. Without adequate manganese, steel becomes weak and brittle. Allied strategic bombing compounded the crisis. In 1943, British and American bombers struck the Knaben mine in Norway, destroying Germany's primary source of molybdenum. Backup supplies from Finland and Japan were interdicted by Allied naval operations. Molybdenum was crucial for maintaining toughness in armor plate and preventing temper brittleness during heat treatment. German metallurgists scrambled to compensate. They increased chromium content, hoping higher hardness would offset reduced toughness. They substituted vanadium from molybdenum where possible. Most critically, in summer 1944, they switched to high-carbon steel alloyed with nickel in an attempt to maintain strength. This decision was catastrophic. High-carbon steel with elevated chromium and insufficient molybdenum produces armor that is extremely hard but dangerously brittle. The nickel addition intended to improve toughness instead combined with the high carbon content to make the armor even more prone to cracking, especially at weld seams. Quality control collapsed simultaneously. Allied bombing disrupted not just raw material supplies, but also the carefully controlled heat treating processes that turned raw steel into armor. Plates that should have been heated to 1200 to 1700 degrees Fahrenheit and then properly quenched were instead improperly tempered, cooled too slowly, or heated inconsistently. Soviet technical reports from 1945 noted with scientific precision. The Germans do not have a fracture test for quality control of heat treatment. A wide range of fractures indicates that the process, if it is established at all, is not being followed. The Panther's armor wasn't just being penetrated, it was falling apart. The degradation wasn't uniform. That's what made it so insidious. A Panther produced at Mann's Nuremberg factory in early 1943 might have armor that met specifications, with proper alloy content and heat treatment. But a Panther rolling off the assembly line at Daimler-Benz in late 1944 could have armor with wildly different chemical composition, inadequate tempering, and welds that would fail under the first serious impact. American metallurgists documented the variations in captured Panthers. Sulfur content, which should have been kept below 0.05% to prevent brittleness, was found at 0.22%. Chromium content varied from 1.25% to over 2.13% in different plates. Manganese levels ranged from acceptable to 3 times the required amount. There was no consistency, no standardization, no quality control. The surface-hardened face of Panther armor, created through flame hardening with oxyacetylene torches, added another layer of complexity. This heterogeneous armor was supposed to shatter incoming projectiles against its ultra-hard surface layer, while the softer backing absorbed the impact energy. But surface hardening only works if the base steel is properly formulated. With degraded steel quality and improper heat treatment, the hard surface layer became a liability. Instead of deflecting shells, it spalled catastrophically when struck, sending razor-sharp fragments through the interior of the tank. German field commanders noticed the problems but couldn't articulate the cause. They reported Panthers being knocked out by hits that should have been survivable. Maintenance crews found stress cracks appearing in armor plates that had never seen combat. Welds failed during routine operations. By November 1944, even Panzer Ace crews who had survived dozens of engagements reported a troubling trend. Panthers built earlier in the war could absorb punishment. Later production models seemed fragile, unreliable, prone to catastrophic failures. But German tank crews weren't metallurgists. They couldn't know that when a Soviet 122mm shell struck their glacis plate and penetrated at 2,500 meters, a distance that should have been safe, it wasn't just the shell that had improved. Their own armor was betraying them. December 1944. The Ardennes Offensive. Operation Watch on the Rhine. Hitler's desperate gamble to split Allied forces in Belgium. German armored formations, including numerous Panther tanks, launched a surprise attack through the densely forested Ardennes. For the first time, American tank destroyer crews with 90mm guns and the new T-33 ammunition faced Panthers in large-scale combat. The results were nothing short of revolutionary. Lieutenant Alfred Rose of the 814th Tank Destroyer Battalion scored a kill against a Panther at 4,600 yards, the maximum range of his telescopic sight. The T-33 shell struck the glacis plate and penetrated cleanly. At that distance, the Panther crew probably never even saw the M36 that killed them. But not every engagement went smoothly. American crews discovered that even with T-33 ammunition, the Panther's glacis could still deflect shots at certain angles, especially at very close range, where the shell's trajectory was too flat. At 150 yards, one Panther deflected a 90mm round that struck at an extreme angle. The lesson was clear. T-33 could defeat the Panther's frontal armor reliably, but shot placement still mattered. Perpendicular hits or near-perpendicular hits were lethal. Extreme angles could still result in deflections. On the Eastern Front, similar revelations were unfolding. IS-2 crews, who had spent months frustrated by ricochets and non-penetrations, suddenly found their 122mm guns devastatingly effective. Panthers that withstood hits at 700 meters in summer 1944 were being penetrated at 2,500 meters in winter. One Soviet combat report described a BR-471 round striking a Panther's glacis at extreme range. Instead of simply penetrating, the shell caused the entire front armor plate to fracture along the weld seams. The force of the impact literally tore the glacis plate loose from the hull. British Firefly crews in Northwest Europe, armed with 17-pounder APDS, found they could engage Panthers frontally with confidence at ranges under 400 yards. The accuracy problems that plagued APDS at longer distances were irrelevant in the close-quarters fighting through Dutch towns and German cities. The Panther's reputation as an invincible killing machine was crumbling, not just because Allied ammunition had improved, but because the Panthers themselves were no longer built to the same standard. Tank crews began to notice the difference themselves. Veterans who had commanded early production Panthers in 1943 und dann Late Production Models in 1945 reportete einen starken Decline in Survivability. Hauptmann Wilhelm Meyer, ein Panther Company Commander, noted in his diary in Januar 1945: Die neue Panthers von der Fabrik sind nicht dieselbe. Hits, die an meinem ersten Panther in Kurs nun aufgehalten hätten, penetrieren. Das Armor ringt different, wenn es schlägt. Irgendetwas hat sich verändert. He was right, aber er konnte nicht die volle Geschichte erzählen. Die metallurgische Degradation war nur halb die Äquation. Die andere halbe war, dass Allied-Ammunitionsdesigner hatten bereits über ein Jahr gecapturete Panther-Armor entstudiert, lernen seine Schwächen, optimieren deren Shells, um every flaw zu exploitieren. Der amerikanische T-33-Round war nicht nur härter als Standard-AP-Shot, es featurete einen redesigned Ogive, den Kurven-Nose der Shell, specifically calculated to minimize deflection against sloped armor. Die Heat-Treatment-Process war meticulously controlled, zu kreieren eine Shell, die wahrhaft ist, um Armor zu penetrieren, aber genug tough ist, um nicht auf Impact zu shattern. British metallurgists made similar improvements zu ihren APDS penetrators, doch die Akkuratsproblem konnten sie nicht voll umfassen. Sowjet-Engineers perfektionierten den BR-471B mit seinem revolutionären Blunt-Nose-Design. But perhaps the most significant factor was one that no amount of engineering could have predicted. Die Germanen waren literally raus aus den Materialien, um propere Armor zu machen. By March 1945, German armor steel specifications abandoned requirements für Molybdenum und Vanadium entgegen. Nickel wurde reserviert nur für die dicksten Platten. Der meinallierende Element war Chromium, was erhöhte Hartheit gab, aber ohne propere Balancing-Elemente machte den Stahl katastrophal brittle. Allied intelligence officers examining Panthers destroyed in the final months of the war found armor das fractured like ceramic. In some cases, 75 mm high explosive shells, not even armor-piercing rounds, waren cracking plates und blowing sections of armor completely off the vehicle. Der Panther hat gone from Germanys Antwort zu den T-34 zu einem Vehikel mit Armor, das könnte frontal getroffen werden von Waffen, die es einst Schrock-off mit Contempt aufmachte. Die invincible Tank hat gewonnen vulnerabel. Die Frage war, did German High Command know?
The answer is yes, they knew, and they were terrified. Classified German documents recovered after the war revealed that Wehrmacht ordnance officials were acutely aware of the armor quality crisis as early as mid-1944. A WA-Proof 1 report from October 1944 showed German engineers conducting their own tests of Allied ammunition against Panther armor. The report contained penetration data for Soviet 122 mm guns and made tactical recommendations. Panthers should close to within 600 meters to guarantee penetration of IS-2 frontal armor, while IS-2s could penetrate Panthers at 1,000 meters. But buried in the report's appendices were notes that Allied intelligence wouldn't discover until 1946. German testers acknowledged that the Panther armor plates they were using for ballistic trials were showing inconsistent resistance properties, and that plate quality varies significantly between production batches. They knew their armor was failing. They couldn't stop it. Production quotas demanded 380 Panthers per month at peak. There was no time for proper quality control, no time to source proper alloying elements, no time to conduct metallurgical testing on every plate. The alternative was to reduce production, which was politically and militarily impossible. So defective Panthers rolled off assembly lines and were shipped directly to the front. Tank crews received vehicles with armor that might withstand a dozen hits or might fracture catastrophically from the first shell strike. There was no way to know which. Some German metallurgists proposed solutions: reduce plate thickness but improve quality, switch to homogeneous armor instead of face-hardened, redesigned the glacis angle to compensate for weaker steel. Every proposal was rejected. Changing production methods during wartime was deemed too disruptive. Instead, German tactical doctrine adapted. Panthers were instructed to maintain even greater standoff distances from enemy tanks. They were to avoid frontal engagements whenever possible. Tank commanders were told to prioritize fighting from ambush positions rather than mobile combat. In other words, the Panther, designed as a fast, mobile tank destroyer, was being used as a static defensive weapon, not because of tactical preference, but because the armor could no longer be trusted. The secret was out, at least within German command. But Allied tank crews still had to discover it the hard way, one engagement at a time. March 1945. The final battles in Germany. Allied forces were crossing the Rhine, and Panther tanks were thrown into desperate last-ditch defenses. American M36 crews discovered that late-war Panthers were markedly easier to kill than earlier models. One tank destroyer commander reported, "Panthers we encountered in the Ardennes could sometimes survive multiple hits. Panthers we're facing now die on the first or second shot, even at range." Soviet IS-2 and ISU-122 crews made similar observations. Combat reports from the Battle of Berlin described 122mm shells penetrating Panther glacis plates at ranges exceeding 2,000 meters, distances where penetration should have been theoretically impossible according to 1943 ballistic calculations. British forces advancing through northern Germany encountered Panthers that had been abandoned not because of mechanical failure or combat damage, but because armor plates had fractured during routine movements. Stress cracks appeared spontaneously in welds. In one documented case, a Panther's glacis plate literally fell off the vehicle while it was being driven to a defensive position. The degradation had reached critical levels. American ordnance officers examining Panthers captured in April 1945 found armor with chemical compositions that barely qualified as steel. Carbon content exceeded 0.75% in some plates, far beyond acceptable limits. Chromium levels were inconsistent. Nickel was virtually absent in most plates except the turret. One metallurgist's report stated bluntly, "This armor would be rejected for use in any American vehicle. It is brittle, poorly welded, and exhibits fracture characteristics similar to cast iron." Yet these were the tanks Germany was deploying to defend its homeland. Panthers with armor so compromised that even 76mm guns, which struggled against 1943 production Panthers, could penetrate the glacis at moderate ranges. The T-33 shell, the 17-pounder APDS, the BR-471B, all three contributed to defeating the Panther. But the fourth and most decisive factor was one the Allies never designed: Germany's own material shortages and quality control collapse. The Panther's front plate didn't just become penetrable, it became a death trap. The hidden truth about late-war Panther armor quality remained largely classified for decades after the war. Why? Because revealing the extent of German armor degradation would have exposed how close Germany came to total material collapse in 1944, information that Cold War intelligence agencies wanted to keep secret while they assessed Soviet capabilities. It would also have revealed uncomfortable truths about Allied ammunition development. The fact that British APDS, despite its theoretical superiority, remained practically ineffective beyond 400 yards wasn't something post-war military establishments wanted to advertise. The American T-33 round was quietly incorporated into Cold War tank destroyer doctrine, but the specific metallurgical advantages that made it effective against late-war German armor were never fully publicized. Military engineers knew that future enemies would not make the same mistakes as desperate Germans in 1945. Soviet development of the BR-471B was classified even more deeply. The revelation that blunt-nosed projectiles could outperform sharp-nosed ones against sloped armor contradicted decades of armor-piercing theory. It wasn't until post-war testing in the 1960s that Western ballistics experts fully understood why the Soviet approach worked. What emerged in the 1970s and 80s, as documents were gradually declassified, was a more complex picture than the wartime narrative of invincible Panthers defeated by superior Allied engineering. The reality was messier. German armor quality collapsed due to material shortages and quality control failures. Allied ammunition improved through systematic testing and metallurgical refinement. Both factors contributed equally. The Panther remained a dangerous opponent until the last day of the war. A well-built early production Panther with proper armor could still deflect most Allied shells from the front. But by 1945, the odds of encountering one of these properly built Panthers had dropped dramatically. American tank destroyer crews joked darkly. Early war Panthers are tigers. Late war Panthers are target practice. The joke was grounded in truth. The same Panther design that terrorized Soviet tank crews at Kursk in 1943 had become vulnerable to frontal penetration by weapons it once shrugged off. Not because the design failed, but because the materials and manufacturing could no longer support it.
The aftermath of the Panther armor crisis shaped tank design for decades. American post-war tank development emphasized reliability and manufacturability over maximum armor thickness. The lessons of German quality control collapse were clear. Better to have adequate armor that could be produced consistently than theoretical maximum protection that couldn't be maintained under wartime conditions. The M26 Pershing and its successors featured thinner armor than German heavy tanks, but used carefully quality-controlled rolled homogeneous armor. American metallurgists established strict testing protocols. Every armor plate was subjected to ballistic testing, every weld was inspected, every heat treatment cycle was monitored. Soviet tank design went in the opposite direction. Convinced that heavy shells like the 122 mm had proven their worth against even degraded German armor, the USSR continued developing heavy tanks through the IS-3, IS-4, and eventually the T-10. But Soviet metallurgists also learned from German failures. They established rigid quality control standards and maintained stockpiles of critical alloying elements. British tank development incorporated the lessons of APDS accuracy problems. Post-war shells featured stabilizing fins and improved sabot designs. The 20-pounder gun that equipped the Centurion used APDS ammunition with dramatically better accuracy than wartime versions. Germany's own post-war tank development, when West Germany was rearmed in the 1950s, showed how deeply the Panther's metallurgical failures had been internalized. The Leopard 1 tank, introduced in 1965, used relatively thin armor and relied on mobility and firepower rather than heavy protection, a direct rejection of the Panther philosophy. The T-33 round itself saw limited post-war service. By the 1950s, heat, high-explosive anti-tank rounds, and improved APDS designs made conventional armor-piercing shot obsolete. But the metallurgical principles that made T-33 effective, controlled hardness, optimized nose shape, resistance to shattering, became foundational to all subsequent armor-piercing ammunition design. The Panther's armor, once considered the pinnacle of protection, became a cautionary tale taught in every military engineering school. Maximum theoretical performance is meaningless if you can't manufacture it consistently at scale under wartime conditions.
Today, preserved Panthers sit in museums around the world. Visitors marvel at the massive glacis plate, the sophisticated suspension, the powerful 75mm gun. What they can't see is the story hidden in the steel itself. Some of these museum Panthers have early war armor that still rings with the distinctive tone of properly treated high-quality steel. Others have late war armor that, when examined metallurgically, reveals the compromises and shortcuts of a desperate regime running out of materials and time. Modern armor technology has moved far beyond World War II steel plates. Composite armor, reactive armor, and active protection systems have made the concept of impenetrable frontal armor obsolete. No modern main battle tank relies solely on passive armor to survive. But the fundamental lesson of the Panther's front plate remains relevant. In military technology, the ability to manufacture and maintain equipment consistently is as important as the theoretical performance of the design itself. The three shells that defeated the Panther, British APDS, American T-33, and Soviet BR-471B, represented three different approaches to the same problem. All three worked, but all three had limitations. The British solution offered maximum penetration but suffered from accuracy problems. The American solution provided reliable effectiveness but required perfect metallurgy. The Soviet solution worked brilliantly but arrived too late. The fourth factor, German armor degradation, was never a weapon the Allies could deploy. It was a consequence of strategic bombing, resource denial, and the grinding attrition of total war. But it was perhaps the most decisive factor of all. The Panther's front plate wasn't defeated by a single unknown shell. It was defeated by the intersection of Allied metallurgical ingenuity, German material collapse, and the inexorable mathematics of industrial warfare. If you found this deep dive into armored warfare fascinating, check out our video on how Allied codebreakers tracked Panther production through intercepted railway manifests. And remember to subscribe for more untold technical stories from World War II. Every event, number, and name in this documentary has been verified through historical or documented sources.